a space-time continuous and coercive formulation for the wave equation. And you are welcome to this seminar, as the seminar is going to be discussing the numerical solution of partial differential equation, which I believe is an area that is underexplored in our community. And I would like us to, listen to this very interesting talk by Professor Moiola. But before we start, I will call on Ms. Festa to please read the bio sketch of the author of the lecturer today. And after that, then Professor Moiola can take it up from there. Thank you.
Good afternoon, everyone. Yeah. Andrea Moiola received a PhD in mathematics at the ETH Zurich, Switzerland in 2011. He was then research fellow at the University of Reading, UK, until 2017. When he moved to the University of Pavia, Italy, where he is currently associate professor, his research focuses on numerical methods for the approximation of wave propagation, in particular on Treff's discontinuous Galerkin, boundary element, and space-time method. Thank you.
Okay, so I'll now call on Professor Moiola to share his screen and give us his talk.
Can you see my slides? Can you see the slides?
Yeah, we can see the slides.
I can see the slides, sir.
Thank you very much. This basically we'll talk about the PhD project of Paolo Bignardi, who was a PhD student who finished just a few months ago. So what I'm going to present is basically a summary of this preprint you can find on the arXiv. And there are many more details and extensions in the thesis of Paolo that is online at this address. Please feel free to stop me if the things become too mysterious. Just shout in the microphone and interrupt me. So we are interested in wave equation, in waves in general, and we like simple things. So we like to start from the simplest kind of wave equation, which is the acoustic wave equation, which is a scalar, the sort of prototype of scalar second order linear hyperbolic PDEs. So it's a second derivative in time of a field u minus c squared plus u equals some source term f, where c is just the positive parameter which represents the wave speed. And we assume c to be just a constant. So very simple. What's a typical thing you do when you want to approximate this an initial boundary value problem for this equation? You use method of lines. First, you discretize in space, so discretize the Laplace operator using finite elements, finite differences, whatever, and then you do time stepping. Choose your favorite time stepping scheme. So you treat partial derivatives in space and partial derivatives in time in different ways, with possibly different numerical methods. But we want to do something different. We want to use a space-time method. So to discretize simultaneously derivatives in space and derivatives in time, and treat the partial differential equation as a unique equation without a special difference between the two variables. Why? Well, there are various reasons. The first examples of space-time methods are very old, from maybe the 60s, but they didn't get a lot of success. But in the last 10 or 15 years, there have been a lot of works on space-time methods maybe more on parabolic PDEs, but also on hyperbolic PDEs. One reason is that we want to have some local mesh refinement in space and time. For instance, imagine this picture here on the right is a space-time domain in where the horizontal direction we have space, in vertical direction we have time, and you have a wave that moves to the right, hits the boundary, bounces back to the left. In some part of the domain, nothing happens, the solution is flat, so you don't want to use a coarse mesh in a finite element scheme, so very few degrees of freedom. In some other parts, you want to refine and put more degrees of freedom, a finer mesh, but the region where something happens, where the profile of the wave is interesting, changes in time, so moves beginning to the right and then to the left. So you like to have to use finite elements with a mesh like this one, with a refinement that is not in the same position in space at all instants in time. So using a mesh of this kind is difficult. It's possible, but it's quite difficult with the method of line, with time stepping. Then you don't want to prescribe a mesh of this kind a priori. You would like your method to figure out what is a good mesh of this kind, so to use some adaptivity. And this is also something that seems to be for which space-time methods can offer some advantages. You want to be able to do some parallelization, some parallel computations. There are many situations where the boundary of your domain evolves in time. So at every instant of time, you want to approximate the solution on a different space domain. And also in this case, using method of line can be complicated. And in some cases, we want to use the tools we know from, or the techniques we know from elliptic PDEs to adapt to hyperbolic equations. And mostly because I come from elliptic PDEs, so these are the tools I know. Okay, so we want to use tools from elliptic PDEs. And so we do a sort of recap of elliptic PDEs or the things we sort of general variational formulation and Galerkin for elliptic PDEs. And just look at simple example, the simplest example. So the prototype elliptic PDEs or boundary value problem for an elliptic PDE is the Dirichlet problem for Poisson equation. So minus Laplace u equal f on some domain omega. You can take as some bounded Lipschitz, for instance, a polygon in the plane with zero boundary condition on the boundary. How do we write a Galerkin method? First, we write a variational formulation. So we take the PDE, we multiply with a test function v, sufficiently smooth and zero the boundary. We integrate by parts, and we get this relation. This is just integration by parts of the Laplacian. Then we look for an element u, which is the known of this problem in H10, so in the Sobolev space of L2 functions with L2 first derivatives and zero boundary condition, such that this equality is true for all possible test functions in the same function space. So this is the variational formulation of the Dirichlet problem. We want to write this in abstract way because then it will be useful to extend this to, for example, to the wave equation. That's our goal. So we can rewrite what is written above here as finding some element u of Hilbert space V, which then this special case is H10, such that a given bilinear form applied to this unknown and some test function V is equal to a right-hand side, a linear functional f applied to the same test function V. So this is just the abstraction of the line above. Typical Galerkin technique is to choose VH, a finite dimensional subspace of V, and look for an element of this finite dimensional space such that the same equation, the same variational equation written above, is true for all test functions in the same finite dimensional space. So typically in finite elements, you choose VH as a space of piecewise polynomial on a given mesh. But there are plenty of other possible choices. Why is this convenient? Well, a first reason is that you can write this in a very concrete way. You choose a basis function of your discrete space. This space is a space you choose, so you have all can choose it in such a way that you have a simple basis. Choose a basis, and you write a linear system in this form, usual linear algebraic system, where the matrix B has entries corresponding to the valuation of the bilinear form in pairs of elements of the basis. And the right-hand side is the valuation, or each component of the right-hand side is the valuation of one of the right-hand side of the variational problem in one of the basis functions. So you can compute B and F once you know little b and the function of F, and you've chosen your basis. And then when you solve this linear system, the vector U gives the coefficient in the linear combination of the basis function that gives the solution of the Galerkin method. So these are two different ways. This one and this one are equivalent ways of writing the same, exactly the same method. This is the sort of the way we used to define it and to analyze it, and the second is how we implement it. But the Galerkin method is interesting for this kind of problems because gives immediately a well-posed and quasi-optimal linear system for all possible finite dimensional subspaces VH. So if you want to solve this Poisson problem, you have the ambient space V is H10. You take any, you partition the domain omega in triangles, Florin 2D. You take any triangulation of omega, take any space of piecewise polynomials on this triangulation, and you can assemble Galerkin, and this will be well posed in the sense that the matrix of this system is invertible. You press solve on your computer and you get a solution. It's not, there is no risk of getting singular systems and so on. Why is this? This is true because of Lax-Milgram theorem. And this requires two different conditions: continuity and coercivity of the bilinear form B. Continuity simply means that the bilinear form is bounded by the norm of the arguments, the norm in V, which is the ambient space, so H1 in this case. And typically, this can always be satisfied. You choose the norm in such a way that this is continuous. Second, you need coercivity. Coercivity means that then when you write the bilinear form in the same element twice, so you compute in the same element twice, BB, then what you get is positive and is bounded below by a positive number, the coercivity coefficient, and the square of the norm of the argument, where the norm here must be the same as the continuity norm. These are we call it coercivity, sometimes called the sign definiteness, is the same, is a positivity property of this bilinear form. Lax-Milgram theorem says exactly that once you have these two properties, then the linear system arising from the Galerkin method is invertible, so the method is well posed. You can always compute a solution. Then the second property that follows from Lax-Milgram is the quasi-optimality that I mentioned before, which is this inequality you see here at the bottom. quasi-optimality says that the error committed by the Galerkin method is bounded by the best approximation error. This inf is the best error, the smallest error you could commit if you were able to choose if you knew the exact solution you, and if you could choose the best element in your, say, piecewise polynomial space. So this is the best you can hope for, this inf, once you have chosen your space VH here. Galerkin method is quasi-optimal in the sense that the error committed can be larger than this just by a constant factor, and this constant factor is this ratio CB over gamma B, which is the ratio between the continuity and the coercivity constant. Okay. So here the point is that to get all these good properties, we need continuity and coercivity of the bilinear form respect to some norm. This is very simple for Poisson, more complicated for more complicated problems. In particular, for the wave equation in space-time, seems impossible to get coercivity. Why? Well, differently from Poisson, the wave equation involves a difference between second derivatives. So the second derivative in time and the Laplacian have opposite sign. There is a minus sign inside here. So when you multiply with a test function and you integrate by parts in the space-time cylinder, now Q is a domain in space and time. When you integrate by parts, you change both signs, but you can turn this equation as you wish, but one will have one term, the term coming from the time derivatives. Yep. Sorry. We always have opposite signs. One has to be positive, one has to be negative. So it's impossible to bound from below with something positive for all v. Depending on which of these two terms, time derivatives or gradient will dominate, you will have something either positive or negative. For some v positive, so for some other v negative. So how can we get a continuous and coercive space-time variational formulation for this equation with some boundary condition? Doesn't look very plausible. And indeed, as I said, there are a lot of space-time schemes, numerical schemes available, but most of them are discontinuous Galerkin, so they don't fit this framework. They start from different premises that you have to you partition the domain, and you don't yeah, they're not part of the general scheme we have seen before. So what we're talking about is called conforming Galerkin, and there are some methods, space-time discretization based on conforming Galerkin. For instance, there are some papers by Olaf Steinbach and Marco Zank in Austria, but they have a strong restriction. They need tensor products, discrete spaces, which means that the discretization in space and time are independent, and if you refine the mesh in some region in space, you have to keep the same refinement for all times. So how can we get this? This looks implausible, but looks implausible also for another equation. This may be a bit simpler, the Helmholtz equation, which is Laplace u plus k squared u, where k is a positive number, is a large number, say. Where does the Helmholtz equation comes from? Is also an equation that models acoustic waves, but in time harmonic regimes. If you have a solution u of the wave equation that is time harmonic in the sense that can be written in this way as a real part of a complex exponential times a function that depends only on u. So you prescribe a sinusoidal dependence in time with a given time frequency omega, then the space dependence of this wave solution is solution of the Helmholtz equation. So it's closely related to the wave equation. It's a Fourier transform in time of the wave equation. But here there is no time dependence because the time dependence has been factored out in this exponential. So this is an elliptic PD, but is an indefinite elliptic PD because of the sign that appear. When you multiply with a function v and you integrate by parts, you get something with a sign and something with the opposite sign. The gradient and the zero order term have opposite sign. So apparently, also in this case, it's difficult to, it's impossible to bound this from below. But several years ago, together with the colleague Johan Spence from Bath, we found a coercive formulation for this Helmholtz equation, for some boundary value problem for the Helmholtz equation. And so we want to adapt this technique to the space-time wave equation. What was the trick for this result? The trick was to use something called Relic or Morawetz multiplier. Let me show you what they are. These basically are consisting doing integration by parts with a special test function. A function is called multiplier because it's multiplied to u. So instead of taking just another function in the same space, we want to include some operator. These were used by Relic in the 40s for very different purposes related to waves, and then by Morawetz in the 60s in the context of wave propagation and scattering theory. And she didn't care about numerical methods and about coercive formulation, but she was using these multipliers to study the time dependence of some energy functional of the solution of a scattering problem, and to study how the energy decay in some geometrical settings. So I want to show how we can adapt these Morawetz multipliers to our purposes to get a formulation. So this slide is very abstract, is sort of the general framework that we follow both for Helmholtz and for the wave equation. So imagine you want to solve some boundary value problem in this form, where L is a linear differential operator, for instance, the wave operator applied to some unknown u with a source term f on some domain, and B represent all the boundary conditions. So if this could be only in space or could be in space-time. So in this case, if D is a space-time domain, then B includes both the boundary and the initial conditions. We have to make three choices. First, we need to choose a multiplier, which is an operator from V is just a function space where we expect to find U into L2 of the domain. Then will be something very simple. We show in the concrete case for the wave equation what it is. It's just some operator, some differential operator, some combination of partial derivatives of the argument. Then we want to write the integral over the domain where the problem is posed of the product between the operator of the PD applied to a function u, and this multiplier applied to another function v plus the symmetric term. So here we're swapping n and l. One is applied to u and the other to v. So the second choice we have to make is a decomposition. We want to manipulate this integral using integration by parts in such a way that we can split it in two terms. One we call it R, the other we call it S, and S is a term that can be computed only from V once we know that U satisfies the boundary condition. So basically, after integration by parts, here we are collecting all the terms that contain the boundary data on U. So G, the coefficient, or the boundary condition G. There are several ways of splitting this integral into terms of this kind. And then that is sort of less relevant. The third thing we need to choose is some penalty bilinear form, some bilinear form that is positive semi-definite, so non-negative, and corresponding right-hand side in such a way that the U is a solution. We see then what is this in practice, something very simple. And we can also see that we can see easily that U solves a problem, a variational problem in the usual form BUV equal f of V for all test function B, where B and F are defined in this way, using all the ingredients here above. Why? But starting from this identity, we realize that L of U, if U is to be the solution of the boundary value problem, is equal to the source term F. So we move this term to the right-hand side of this equation. And so we get this minus F M of V. And this other term S is depends only on the boundary datum G, so we can write it as G of V, so it's independent of U, while the term R of UV, we move it to the left, so it appears here with a minus sign, and then we add these two that are this penalty part. So if you spend 2 minutes thinking about this, it's clear that U is a solution, the solution of this boundary value problem is a solution of this variational problem, but in principle there is no reason to believe that this is coercive. So we want to study how to choose, how to make these choices, and the decomposition R, S, and this L in such a way that this B is coercive. So let's consider, so this was very abstract, let's try to be a bit more concrete. So we have to choose a special initial boundary value problem for the wave equation. So we write the wave equation in a domain Q, which is the Cartesian product of a domain in space. Can be anything, can be an interval in 1D, a polygon in 2D, whatever, times time interval 0t. Initial condition U0 and U1 for the first derivative, and we call omega 0 the space domain at initial time. And we have to choose boundary conditions. We choose impedance boundary condition, which are a linear combination of normal derivative and time derivative. Linear combination with a parameter theta, which is a positive number. Why this boundary condition? Because this is what is most natural in acoustics. Typically, acousticians model obstacles to solid obstacle to acoustic waves with this boundary condition, where and then say they look for U for you represent the acoustic pressure of the wave, and this theta is a parameter that models different kind of materials. So there are characterization of the value of theta for concrete, for metal, for wood, and so on. This is also used in electromagnetics to model non-perfect conductors. And from mathematical point of view is interesting because this boundary condition absorbs part of the energy of the wave. When a wave hits a boundary with this impedance condition, is typically partly reflected, partly transmitted outside and absorbed by the boundary. The wave operator, so second derivative in time minus Laplace. We need to define, we have to choose a multiplier, and we choose a very simple thing. This multiplier, m of v, is just a linear combination of the radial derivative of v, so gradient scalar position vector x, and the time derivative. The time derivative is weighted with this coefficient, which is t time minus final time, and there are three coefficients, xi, beta, and nu, which are just numbers that we need to choose. So this is basically a first order derivative of v with linear coefficients. So nothing complicated. And this is the same kind of multiplier that was used by Morawetz a long time ago to study the energy decay for scattering problems. What do we do with this operator? You remember we wanted to compute the integral of mu w v for two functions uv and vice versa, plus the vice versa. Using basically vector calculus identities, we can prove this identity, this simple vector calculus. Of course, this looks horrible, there are plenty of terms, but this is just chain rule and product rules for the derivative and the divergence. Why is this interesting? Because this is an expansion of this term, that is this sum is what we need for the Morawetz framework, and it allows to write this as a time derivative, a divergence, and something else. So when we integrate over the spacetime domain, the time derivative is integrated to something at initial and final time. The divergence is integrated with the divergence theorem to some flux on the boundary, on the lateral boundary of the domain. And these terms are the product of the time derivatives and the gradients of the two functions u and v, and have these parameters beta, xi, that we can choose to tune the method. Here, maybe I haven't said, d is simply the dimension of the space, where we live 1, 2, 3. So now let's integrate this identity over the space-time cylinder Q. What we get is this, even more horrible, but is a big inequality, but with a very simple structure. This is the integral over the space-time domain Q of this term as some term at initial and final time. Initial time means omega 0 means the space domain at initial time, omega t, same domain, but at the final time. And here we get the term that was in the first bracket here. Then we have on sigma, which is the lateral side of the domain, some flux that depends on the normal vector on the boundary sigma. And then on the volume, we are left with these terms that have that contain some parameters that give us some freedom to choose to get the signs we would like to have. So now we continue with the abstract framework. We have made the first choice, this multiplier. The second choice is the decomposition. I'm not going to write the decomposition because it's some horrible formula, but just want to see the result. And then we need a penalty, this term L. And here, what we need is, hopefully it will be clear later why we need to add these terms to the formulation. This is the a least square term, a residual term. This is the wave operator applied to the trial function u times the wave operator applied to the test function v. This is the just a scalar product at initial time. So these are things we know because wu is the source term f, while u is the initial condition u naught. And we weigh them with two coefficients aq and a omega naught, which are just numerical parameters we can choose. Using these, we can steps that were in the abstract framework, we can write a variational problem. We can say that U is a solution of a variational problem, BUV equal FB, usual form, where B and F have this big expression. So this looks terrible. There are plenty of terms, plenty of integrals, and a lot of terms on each integral, but this is a sum of many terms that are all simple differential operators, or integrals of product of differential operators. We have integrals over the space-time cylinder Q, over the final time, on the lateral boundary, again, the full domain, initial time, full domain, lateral boundary, full domain, initial time. So they're all integrals on different parts of the domain. Good. And what is inside this integral? We have combination of u and v, the two arguments of the bilinear form. Here we have the multiplier, which, as we said before, is just a first-order derivative of v multiplied with coefficients, which are position vector and time variable. So it's not complicated. W is the wave operator. Here we have derivative gradients. We have somewhere where, for instance, here we have a normal derivative on the boundary. So we have all standard derivatives of the various components, various functions u and v. And these look very ugly because we have plenty of coefficients. So there are all these beta, psi, nu, aq, a omega naught, but these are just numbers that we can choose. So these are parameters we can use to adapt the method to what we want to achieve. So this expand the expression and makes everything look more complicated, but at the end they are all, it's a big sum of simple things. So we will prove some continuity and coercivity of this formulation. So we need a norm. What is the natural norm for this? Again, this looks horrible, but is a simple thing. We want to use a norm that is in this form. What is this? The first two terms are basically the L2 norm of the gradient. Here when I write this norm subscript, some domain, I mean L2. So this is the L2 norm of time derivative, L2 norm of the gradient. So this is the H1 norm, the H1 semi-norm in the space-time, weighted with the wave speed just to be dimensionally homogeneous. And then we have the same at initial and final time, and then on the boundary. So these are all L2 norm of time derivatives and space gradient in the volume domain and on its boundary. So nothing too complicated. But then we see the sum of these 6 terms only contain derivatives. So if we give 0 for a constant, so we have to add a term that takes care of the constant. So we add the value, the L2 norm of the function at initial time, in such a way that constant don't give 0 norm. But then we need to add this other term, this W. This is the wave operator. So this contains second order derivatives. Why we need this? Because we want to use this norm to prove the continuity of this the bilinear form B, and then the right hand side F. And here in the bilinear form we have this W, the wave operator, and this is a second order operator, so we need to include it here. So here we have some second order derivatives, but only a second order operator, Laplace minus second derivative in time, and is there, and we have to keep it. So this norm is stronger than H1, but weaker than H2, because there is only this second order derivative. So this norm is chosen simply to control all terms in B and F. Back again, all the terms here can be controlled using Cauchy-Schwarz, only Cauchy-Schwarz, with these terms in this norm. So one can prove the continuities and estimate this constant. But what's the difficult thing here? We want to prove coercivity. What can we do? If we have to make an important assumption, we have to assume that the domain in space, omega, is star-shaped respect to a little ball B delta L. Now, L is the diameter of the domain, the largest segment in the domain omega, and B delta L is a ball of radius, a fraction delta of the diameter. And we want the domain omega to be star-shaped respect to this ball. This means that if you choose any point in this ball and any point in the domain, the segment connecting these 2 points doesn't exit from omega. So basically, you can sit in one of these points in the ball, keep in your hand a laser pointer and point around, and you can point to all points in omega. There are no shadow regions. There are no complicated non-convexities. So this is an extension of convexity, but you can think of convex domains if you prefer as well. Under this assumption, and assuming that the coefficients satisfy some condition, but these conditions are very, very simple. The coefficient psi that enters the multiplier, AQ and the omega 0 that are in the penalty terms just have to be any positive number. Nu has to be larger than 1, and beta has to be larger than something that is computable. Then, under all these assumptions, B, the bilinear form, is bounded below by the norm squared of U times a coefficient that, if you choose the coefficient here in a simple way, is just 1/4 on the star-shapedness parameter. So this is the coercivity of the bilinear form. And this is proved only using Cauchy-Schwarz and simple inequalities. And the star-shapedness enter the story, enter the proofs, simply because it's equivalent to this inequality on the scalar product between the unit normal pointing outside and the position vector x on the boundary. So the star-shapedness gives a lower bound on these, and the boundary terms that are present in B become positive under this assumption, and you get this inequality. So this gives maybe we can skip this, gives the coercivity and so the well-posedness of any conforming Galerkin scheme. This means that we can choose any finite dimensional space Vn in V, here change the notation, sorry, from H to N, and then there exists a unique element in this discrete space such that this equality is true. The variational problem restricted to Vn is satisfied. And this can be computed with the linear system assembled exactly as before. Moreover, the error committed by the Galerkin method is bounded by the best approximation error in times quasi-optimality constant, that if we choose all the coefficients entering the theory in a simple way, is something, just some expression, but is just a number. Depends on delta, the star-shapedness parameter, beta, which is this number here, theta is the impedance parameter in the boundary condition, T is time, final time, L is the diameter of the domain, is something quite simple. So this controls the error in this norm V, which is a very strong norm, which is a good thing because we would like to control the error committed by the method in a strong norm. What is the issue here is that this norm contains this residual term, which has a second derivative, is the wave operator. So we cannot use a standard piecewise polynomial space using finite elements like piecewise linear or so, because the second derivative of a piecewise linear is not in L2. So these are L2 norm. We want this to be well-defined and finite. So if you use piecewise smooth spaces, piecewise polynomials, which is the natural choice to make, and we need to use spaces that are C1. So we need continuity also of the first derivatives, not only of the functions. This is a complication, but it's not too complicated. There are plenty of spaces, discrete spaces that have already been developed and studied since decades. For instance, spaces made of splines, like those from isogeometric analysis. So just some numerical examples. So these are computed in MATLAB. Is just one dimensional space. We have also examples in higher dimensions. And here we're using splines on a regular mesh of quadrilaterals. And here we use cubic splines. This notation means splines of degree 3 in x, splines of degree 3 in time t, so total degrees 6, and C1 continuity. So just two examples. The first one is for a smooth solution where the solution is the sum or the difference, better, of two Gaussian functions. That here x is on the horizontal line, time is in the vertical direction. So these two propagate to the right. They hit the impedance boundary, and they are partly reflected back in the domain. Range of parameters in the formulation. So we want to study first how the solution depend, or the error or the condition number depend on the parameters. So first we fix the simple way all the parameters enters the multiplier, and we want to study the dependence on the two parameters entering the penalty terms. And remember, AQ was the parameter that was multiplied to the residual, the wave operator. And we see that if we plot the L2 error of the solution against AQ, we see this kind of plot, which is something very flat, basically. Once this parameter is, say, smaller than 1, if it's too large, then we run into troubles. But if this parameter is smaller than 1, basically there is some optimal value somewhere here, 10 minus 2, but if we take it very small, at worst, we lose a factor 2 in the error, so not a big deal. This means basically that in practice we can take AQ equal 0, so we can get rid of the second order derivatives in the formulation, and numerically not much changes, while we need this term to be positive in the theory. So this is a sort of suboptimality of the theory. Then here these two plots are showing the error on the left and the condition number in dependence. I don't know if you can read it because it's very small. Dependence on the horizontal line, there is the second parameter A omega naught, and the vertical axis there is AQ. And we see basically here the point is just that this plot don't change much once A omega naught is not very small. So here we have a big region where the error is more or less the same, which means the choice of this parameter is not very delicate. We can choose any point here, you get any choice of parameter here, you get the same result, basically. We can also vary the parameter xi and beta entering the multiplier. Maybe you remember there was a condition on beta that has to be larger than some multiple of xi, and this corresponds to this line. Here I'm plotting relative error on the left and condition number on the right as a function of xi on the abscissas and beta the vertical direction. And once we are above this white line, basically nothing happens. So once we satisfy the conditions coming from the theory, and then you can choose xi and beta as you prefer, and the error is more or less constant. If we take beta too large, the condition number grows, but not in a crazy way. So in this sense, the theory is quite good. And we can plot the convergence of the error. Here, the label is missing, but this is the error when we refine the mesh simultaneously in space and time. On the left, here we see the measure of the error in L2 norm in red, in H1 norm of space-time, and the V norm in green. And here we see, here we're using cubics, so we expect rates 4, 3, and 2 in the three norms. And this is indeed what we obtain. The theory, the coercivity theory gives optimal rates only in the V norm, but we observe numerically the optimal rates also in the weaker norm, L2 and H1, which are also the most interesting norms in practice. One can wonder then if the method is really unconditionally stable. This comes from the theory because there is no assumption on the choice of the discrete space on the mesh. And here, maybe this plot is difficult to interpret. We are fixing the time step, and here we plot the error in the norm H1 and L2 against the ratio between HT and HX. So the step in time and the step in space. So decreasing the step in X. So increasing this ratio, we see that the error improves for a while, and then the error committed by the time discretization becomes dominant, and so the error stops decreasing. So we get something flat, but the important thing is that this doesn't grow, doesn't blow up. So this is very stable. We can do similar things for a singular function. In this case, we have a singularity that propagates inside the domain. So here we have a solution that is continuous, but first derivatives are not continuous, have a discontinuity along this line. And so using high order splines is not general, is not a good idea, but we see that the method is very robust also in this case. We observe some convergence rates also in this case, while other methods are not able to get any convergence for such a singular function. So just to summarize, sorry, bit late. To summarize, we have a continuous and coercive space-time formulation for some class of boundary value problem for the wave equation that is derived using Morawetz multipliers. The main assumptions that are needed are the basis function has to be C1 conforming, and the domain has to be star-shaped. There are many other things that Paolo has done and that we would like to do. We can have a more complicated boundary value problem with scatterers inside with Dirichlet boundary conditions. Here we have always assumed constant wave speed, but we can assume that wave speed varies, has to be radially decreasing, but can be smooth, can have jumps, doesn't matter. We haven't tried, but I believe things can be extended to Maxwell, so electromagnetic waves and elastic waves, and also to some more general class of domains. And something that Paolo has done is the extension of this idea to continuous interior penalty. So discretization with C0 finite elements. So lifting this C1 assumption and compensating this lifting with penalty on normal derivatives, more general grades, posteriori error estimation, and adaptivity. We have some theoretical questions that I skipped, and you can find all the information in this, the preprint and in the thesis of Paolo. Thank you for your attention and for your patience and your time. Thank you very much.
Thank you very much for your interesting lecture. And I want to especially thank you because I know the way I tried to get you to this place, because I know you are very busy.
Yeah, no worries.
Yeah, and I thank you, and it was very impromptu, and you answered us and tried to share your research with us. I want to really thank you for the very interesting lecture. Now we will now welcome some comments or questions from the participants. If you have questions, please just click on your react button and just give us a reaction. Raise up your hands and we'll call you to ask the question. Any questions from our participants? PhD students, master students working in partial differential equations. If you have questions or you want clarification on some things, you could just raise up your hands and I'll call you to ask questions. Okay, if there are no questions, maybe I'll just call on just to inform us that the director of the National Mathematical Center is here with us today, and I think I could see Professor Ario too on the participant list. So maybe I just give the director of the Mathematical Center, Professor, maybe promised to give us maybe a word. Then maybe Professor Ario too should just give us some remarks, and then we can go. Director, sir. Director, sir, are you with us, sir? Okay. Professor Ario, please, could you just give us a remark or a comment on...
I have a question, please.
Okay, please ask your question, please. Thank you.
Okay, I would like to thank the professor for this nice presentation. I'm Martial. I'm doing numerical analysis on manifold, numerical analysis of PDE on manifold. I studied the case where the manifold is regular and the case where the manifold is just Lipschitz. I would like to know if this one can be extended to the manifold.
That's a good question. I think to some extent, yes. Probably to simple kind of yes, the geometry of the problem is important. So you need yeah, you can interpret the wave speed as a metric in the manifold, and then you get some constraint on the metric, but for sure can be extended to some cases. In the preprint there is nothing in this direction, but Paolo wrote something in the thesis, or some section on the thesis on variable coefficients, and this can be pulled back to some some manifolds now. Difficult to say sort of logically which kind of manifolds you need, but for sure there is not a problem of regularity. Lipschitz or non-Lipschitz doesn't matter. It's a matter of monotonicity of the metric coefficient. There is what I said here in just one word, a radially decreasing wave speed. But for sure there is space for doing something in this direction.
Yeah, okay. If some collaboration is needed, it is welcome. If it is possible, we can
Maybe, yes.
be in touch.
Okay. Okay, so Professor Moiola, please, could you help us maybe type your email address on the chat box? Maybe if we could reach you out if there's something they could do.
Yes, I can put it in the chat.
Thank you.
Hello, good afternoon.
Director, sir, are you with us, sir?
Yes, I'm with you. Sorry, I was off.
Oh,
I'm
okay.
back now.
Thank you. Okay, please, sir, I would like you to give a remark on, yes, on this, sir.
All right, I want to thank you very much for inviting persons that are well known in their fields. I think it is a very good one for us. And I also want to thank the person that presented. I think it's a very good one. But my own question or per se is it possible to apply these to variable coefficients? That's my question. Thank you.
Yes, the condition is this one is, oops, sorry. We need the wave speed to be increasing radially because we need to avoid trapping of rays and say that there is a simple extension to radially decreasing coefficients, and this is already in the thesis of Paolo. For more general coefficients that avoid trapping is maybe possible, but more complicated. You have to choose a more complicated multipliers that follow the light rays, the trajectory of rays or particles with the B characteristic associated to the material coefficients, say.
Thank you.
Okay. Thank you very much, sir. Okay, so I have put on the chat box a form that you can click if you want to receive the materials and the videos of this talk. Also, I've put on the chat box a link to the PhD thesis of Paolo. So you can just click that and get the, maybe find something to read from the thesis. And in the absence of no question, now let me, yes, I think I should say this. So recently I was introduced to a professor from the University of Oxford, Professor Patrick Farrell, who has agreed to join me in co-organizing this seminar series. So he'll be joining us in the next seminar series in June. I'll be introducing him formally to us, and he's going to help us to also get some speakers and also to help us plan some programs in the future. So this is just an update and just to make us understand that we are actually pushing forward and trying to change the narrative of numerical analysis in Nigeria, and we are trying to see how we can help young PhD students and early career researchers in numerical analysis, so that we can continue to collaborate, share ideas, and improve on our research and results. And I will also ask maybe Professor Moiola, maybe after the talk, I will send you an email so that you can send us your slides.
Yeah, I will send you the slide. I will send you. No.
Thank you very much. Okay, so in the absence of no question, yes, so I think I want to thank everybody for coming for this seminar series of May. And I want to wish you all well in your research, and I want to pray that God continue to help you, guide you, and give you directions and ideas in your areas of research and help you. And if you have problems with your research, please feel free to reach out to me, and I can help you or connect you to people that are working in those areas, and they can find solution for you. Thank you very much for coming today. See you in June. Bye-bye.
Thank you for
Professor
the invitation. Thanks,
Moiola, thank you so
everybody.
much. Thank you very much, please. Thank you. I really appreciate you. Thank you so much.
No worries. Thanks to you.
Bye-bye.
Bye-bye.
Bye-bye.